know he's busy now. I will open the seminar. So, our seminar, as you know, is a joint seminar between the Faculty of Electronics in Technical University of Sofia and also the Bulgarian sections of IEEE. Now, the lecture will be from Professor St.Burrow, he's here, from University of Bristol, and the subject will be nonlinear vibration in energy harvesting. Maybe some of you have read the biography of Professor Dr. Burrow, but let me repeat and to present Dr. Burrow. So, Dr. Steve Burrow received his PhD in 2002 from the Department of Electrical and Electronic Engineering, University of Bristol, for work in modeling of interaction between electromagnetic loudspeakers and switched mode amplifiers. He remained in the department, reaching novel machines and drive topologies for aircraft generator application before moving to the Department of Aerospace Engineering in 2004 to lecture on avionics systems. He was promoted to reader in 2012 and currently coordinates avionics teaching within Aerospace Engineering department and is also an admission tutor for home students. He manages a team of researchers encompassing a range of projects including subglacial sensing, energy harvesting, structural health monitoring, and the more electric aircraft. His research has received funding from APSRC, NERC, etc., and from the industry. So now, Professor Burrow, yes.
Well, thank you very much for coming and having me here to give this talk. It's fairly short notice. Some of you may know I've come with a colleague, a technical colleague, and because we're thinking of running an international conference in Bulgaria in 2019. So part of this trip is a scoping out trip to see what people are doing here and to look at venues. My background is as an electrical engineer, but for the last sort of maybe 10-15 years I've been looking at energy harvesting technologies. And energy harvesting and the associated technologies are key to the Power MEMS conference, which we would like to hold here in 2 years' time. So I thought it was fitting to give this presentation on those technologies. And one of the reasons I like giving this presentation is it's really a summary of the work I was doing over 10 years. And as is common with research, it doesn't necessarily have a happy ending, but we did some interesting work along the way. So right at the beginning, where did we start? So in early 2005, we were working with Augusta Westland, who are a major rotary wing aircraft manufacturer, to monitor the blade, so structural health monitoring of the blades. We were looking at, could we determine the lifetime, could we do health prognostics on the blade. And in order to do that, we wanted to put a wireless sensor in the rotating parts here that would be embedded for life, for the lifetime of the blade. And then somewhere in the avionics bay, we would have a data concentrator that was collecting wireless data. And we had an architecture, so there was some sensing element, some sort of feature extraction that was correlating what we measured with wear on the component, and then a wireless transceiver unit. And this had sort of consumptions that were in the order of tens of milliwatts, sometimes high tens of milliwatts. And when you look on a helicopter has a great deal of vibration. And so it seemed to make sense that we could use these sort of vibration levels. So these two graphs are the vibration that are measured by the helicopter airframe, and you can see that in certain locations here in pink we're getting up to 4G of acceleration at multiples of the blade pass frequency. So it's a very energetic environment on board the helicopter. So I like to show some videos that they're not directly connected, but they are kind of interesting, just to reinforce this idea that helicopters vibrate a great deal. And it's necessary to design the structure to avoid resonances. This is a finite element wireframe model of a Lynx helicopter showing the principal modes of vibration. And when you're designing the frame, you try and avoid resonances that are harmonically related to the fixed rotor speed. So these are exaggerated. So why they are really important for helicopters is illustrated in the next video I'd like to show you. Some of you may have, has anyone seen this video? It's available on YouTube, and it's an example of ground resonance of a helicopter. This is a tandem rotor Chinook helicopter that was being used for ballistic tests, and it was strapped down, and the intention was to fire at it while it was running. But before they could do that, this happened. It essentially tore itself apart from ground resonance. Incidentally, in normal operation, you would take off to prevent the ground resonance getting to that stage, but because they've tied it down, they were unable to do so. But I hope anyway I've articulated an environment that's very energetic, there's lots of vibration, but there's also lots of safety critical parts that we need to monitor and understand. This is the electronics that we developed at that time. So these are non-flying electronics, but we were measuring things like acceleration. We had piezoelectric strain sensors, temperature sensors, and an azimuth sensor which measures the rotation of the blade. To get the power consumption down as low as possible, we would do what we term analog signal processing, but really that is filtering, so narrowband filtering to select particular frequency components from the signal. And then we went into a microcontrol, and this was based on a Texas Instruments MSP 430, and it would run particular algorithms. So we were looking at synchronous time averaging, which is a type of time domain comb filtering type operation, and also running other frequency domain algorithms to extract components. And we wanted this to be powered by energy harvesting, but we'll talk about why we wanted it to be power harvesting in the next few slides. So this is the power consumption of this device. So periodically it would have a maintenance pulse telling the base station that it was still there. Then it would sample its signals, and then it would transmit. And this was customizable to a degree depending on the operation that you required. But it meant that the average power when it was active is about 3 milliwatts, so over the long term a 3 milliwatt power consumption. And when it was sampling and transmitting during this 10-second period, it was about 90 milliwatts. But we might do that sampling and transmission once every minute or once every 2 or 3 minutes, depending on what we have. And so now we have some figures. We can do an interesting exercise to say, how could we power this other than energy harvesting? If we wanted to use an electrochemical battery, what numbers fall out? So the design life of a blade is about 1,000 hours, something like that. So we would like our embedded electronics to last for 1,000 hours without intervention. We're assuming that our wireless node, wireless system can sleep in between flights. Now that, if you have worked in this field, you know that's not necessarily realistic, because waking up wireless sensors is difficult. Obviously consume power, but let's be as generous as we can, and let's assume that we can make our node sleep between flights. And we're going to do one sampling, processing, transmission event every minute. So if you work through those sums, you end up with a lifetime consumption of 17 watt-hours for this electronic node that we would like to embed within the blade. So what does that mean? If you're doing it with a cell, then in theory something like this, a lithium thionyl chloride D cell, that will suffice, and that has 45 grams and 26 milliliters of volume, which maybe seems like that's possible. But remember, this is a pulsed load, and it's living on the rotor head, which gets very hot and very cold. So when you derate the temperature and the pulse load, you actually need 4 of them. So that's quite a large size. Now you might also have some concerns about using lithium thionyl chloride, which is a gel-type electrolyte, on a system that is rotating. You're having centrifugal forces acting on the battery. So if you went to a solid-type electrolyte that are suitable for high G, like a lithium metal oxide, you would end up with 48 AA cells to provide that 17 watt-hours. And so it would weigh nearly a kilogram and have a volume of nearly half a litre. So that is clearly impractical. So if you want to embed electronics within a structure and give it a long lifetime, using primary battery cells is not an option. We need to look for another power source. And this is why energy harvesting is a very desirable thing, even if the technology we have to implement it isn't perhaps as great as we would like. So back to the helicopter, one of the really good things about helicopters for energy harvesting is to avoid all those resonances. The rotors turn at a fixed frequency. And so we can design a vibration energy harvester to work at one of these resonant peaks that we can identify. The sorts of power level that we require in the tens of milliwatts mean that MEMS is too small. So we can start to look at a mesoscale construction, which is more conventional wound coils and magnets. So it's quite easy to build. It's an easy application for energy harvesting. We're making things as easy as possible. If you work through crunch the numbers, then if you have a 10-gram seismic mass being excited at 20 Hertz with 1 G of acceleration, you allow that mass to travel through 10 millimeters, you end up with 30 milliwatts of power being produced. So the numbers seem to stack up. Now some of you might be wondering what these harvesters look like. So here's an example. So a typical vibration harvester is a mass on the end of a spring. It's a simple second order system. So this is our first prototype we made. We have a C core. This is the side view, this is the top view, C core here with a coil, and then a mass with some permanent magnets on a pliant membrane. And this is the very first prototype that we made. Now because aircraft, there's a lot of excitation here, but aircraft are very sensitive to weight, we wanted to try and maximize the flux excursion. We wanted to maximize the load on our magnetic components. And so we used iron here and iron here. And as a sort of consequence of that produced reluctance forces as well as the spring forces. So this design, you have a linear spring here and then a non-linear spring associated with the flux path between the armature and the stator. We didn't at this time realize the consequences of that non-linearity. But one of the other things that is quite good for these designs is that the reluctance forces soften the spring. So this design is very mechanically robust, but in terms of an oscillator it appears quite soft. And that matters when you have something that is spinning on a rotor and there are quite large other forces acting upon it, having something mechanically organized. So what did that do? So the nonlinearity that I described looked something like this. So when there is a large air gap, when the stator and the arch are separated, this is a force displacement graph. You get something like this. And you see there's hysteretic loss as well. So if you make the air gap very small, you can actually create force displacement graphs like this, which is bistable, so it would either sit here or there. We'll look at greater hysteresis, you can see there. And if you look at the frequency response of this, so this is frequency here, and transmissibility here, so amplitude response, you find that it does something very strange. It increases in this direction, and then collapses, and in this direction it follows this one. And it turns out that this is described by a Duffing oscillator. So if we looked in the literature to see where else this might appear, then we found as early as 2001 this microgenerator that was fabricated by Williams et al. Fairly small, 3mm. And what they showed here was as the excitation amplitude was increased, you start to see this folding over of the frequency response, which is a characteristic of nonlinear oscillators. And they at this stage thought that this was a big handicap. You can imagine you're expecting this resonant peak to be replicated at higher amplitudes, but the nonlinearity is rolling off the response. So we built a second prototype to try and explore this, and the hypothesis at this time was perhaps this curved over frequency response could be beneficial because it superficially appears to have a wider bandwidth than a linear oscillator. Maybe this response is really useful. So this was a second generation device. It was built quite large so that we could explore, particularly we could instrument it, and that would have minimal effect on the experiment. But it was really about, could we find a positive aspect of this nonlinearity, not just view it as a negative characteristic. So you can do a bit of analysis of this. So in your mass spring damper system, the nonlinear term is here, it's just a cubic term in the damping. We use, first of all, the harmonic balance method to analyze this, and you can come up with a factor alpha here, which describes the ratio of the nonlinearity to the linear part of the compliance and related to the excitation. And for different values of alpha, you can see that alpha is very small, so it's essentially a linear oscillator. You get a response that's close to a standard linear oscillator. And as you increase alpha, you start to get this bending over of the response. And you can go through and you can determine what we call the jump down point, which is this point here, and the jump up point, which is this point here. This response contains stable and non-stable conditions. So this period here, known as the resonance branch, is stable. This branch here, up to this point, is stable, but this part here is an unstable equilibrium, and the harvester would always, more often than not, end up on this branch. But these are these three conditions that you can be on at this state. Only two of them are stable. So if we looked at the measured response, we found that our experimental harvester was giving us very similar behaviours, and you can start to see how these results were suggesting to us that we could achieve a broadband response, because it appears, at least superficially, as if this harvester, when it's excited with quite a large amplitude excitation, we're getting quite a wide bandwidth here, over 10 Hertz of bandwidth, which is over 50% of the linear resonant frequency. in practical experiments you don't see this unstable branch, which is why this red curve, if you plot it all out, it would have this unstable branch which curls back round down to here. But in physical experiments you don't see that, you just see a drop down, and then as you carry on in this direction you see a jump up. So the big thought was perhaps we could use these harvesters for multi-frequency harvesting, and we did at that time some rather sort of quick and turn out dirty numerical analysis, and we took the harmonic components that we had in our helicopter signal and we put them into a numerical model for this, and it appeared that we would get more energy harvested out than we would from a linear oscillator. It proved that although we published that and it created some discussion, later proved to be an erroneous assumption. If you've ever worked with nonlinear oscillators, you'll know that the phase relation of the components presented to it are critical in order to understand what it will do. And we hadn't sufficiently controlled for that. So at this time, so this was around about 2007, it turned out that there was lots of researchers, very often from the dynamics community, working in these as well. So Einar Harvestland is a big light in the Power Banks conference. He was working on it independently, and some other people, Brian Mann, Abdul Rahman, and Dave Quinn in the US, and Francesco Bottoni in Italy were working on similar systems that had similar characteristics. This is the Brian Mann and Neil Sims device, so they were creating their nonlinearity purely through magnetic suspension, and this was the part that it created quite a level of interest in the dynamics community. This idea that had we found a really positive use for nonlinear oscillators, and since then there are literally hundreds and thousands of papers that have come out. So we refined our analysis even further, and so we could get a closer look. So we have on here the dotted line in black is our experimental data, and the underlying curve is the model data. So we were getting we thought, given the accuracy with which you can measure the nonlinearities in your model, quite a good fit for our behaviours. But the difficulty we were having is it was often quite hard to stay on this resonant branch. Very often your harvester would be here, and then all of a sudden it would inexplicably jump down to this frequency of operation, and this is a sort of a low energy state. This corresponds to a relatively poor energy harvesting performance. We want to be up here. So we plotted the Bayesians of attraction for this oscillator, and this is a phase plot, velocity and displacement, and it basically tells you if you are in the white region at any moment, then you will stay on the high energy branch. If you find yourself in the black region of the phase plot, then you will transition down to the lower energy branch. And what you see is as you go from this 27.5, which is just about, where's that, just about here, as you move up to 35, you find it's almost impossible to stay on the resonant branch. Any small perturbation causes your harvester to be knocked out of this favourable high energy resonant condition and down to the low energy. We then started to look at random vibrations in a more broadband vibrations in a more controlled way. And what we started to find was the performance was pretty poor. So this was a system excited by a narrowband signal with 2 Hz of bandwidth. The center frequency was swept, so a 2 Hz bandwidth that's being swept on the center frequency, and this is shown with the dots, the experimental results here, and you start to see we've lost nearly all of this resonant branch behavior that we were getting previously. The random vibrations causing it to be the perturbation to push it down to the non-resonant branch. It was an unfortunate a realization perhaps that we hadn't got the broadband harvester that we perhaps hoped for. And if you look, we have, so this is the widest, this is 2 Hertz, and we thought perhaps 2 Hertz is quite a wide bandwidth, so let's look at what happens if we constrain it. So we have 2 Hertz broadband excitation, and then 1 Hertz, half a Hertz, and a quarter of a Hertz. And what we found is if there was any deviation in the excitation, so even with only a quarter of a Hertz bandwidth in the excitation, we lost nearly all of that lovely resonant branch operation. One of my students also pursued this and looked at the bistable case, and he produced some lovely experimental work. So this is a restoring force surface for the oscillator. So you plot displacement, velocity, and acceleration is a proxy for force. And this is from measured trajectories, so it's bistable, so you see there's a stable orbit around here, and occasionally it can transition to this stable orbit, and in a higher energy condition it could traverse this orbit. And from these restoring force surfaces you can identify some quite nice characteristics. So if you take a section through in this direction, we can look at the damping of the system, and if you take a section through here, we can plot the compliance response of the system. And what we found with the bistable case is that it was chaotic in many regions. So a frequency response would look something like this, or a chaotic region here and a chaotic region here. But if you looked at the literature at this time, there was hundreds of people publishing on bistable harvesters and really obfuscating with the difficulty in analysing these systems and saying that they were the next best thing, they were great, when really they hadn't taken the time to analyse them properly. We then tried to answer this question of, more rigorously, does a nonlinear harvester have a wider bandwidth than a linear harvester, even notwithstanding the issues we see? So you can simply define for a linear harvester a half power point, the 3 dB power point, and define the bandwidth quite easily. With a nonlinear harvester, you might first think, well, we would just take this condition, but you can argue that that isn't particularly realistic, and maybe that's actually 2 cases within that. You can describe that full bandwidth, and you can say this is the nonlinear harvester bandwidth, or alternatively you could say let's only consider the stable region, and so this is the bandwidth. And so we did some work trying to evaluate this, and if you took essentially a normalized linear harvester and added in some controlled nonlinearity, you can end up with surfaces that look like this. So this is telling you bandwidth on this axis, frequency of excitation, and damping. And the black surface is a linear oscillator, which does what you imagine. So the bandwidth is a function of damping, which is the standard result. It's not a function of frequency. But in the nonlinear case, we find that it's a strong function for both. And it's only in the regions down here, so higher frequency, lower damping, when this red surface is above the black surface, that the nonlinear harvester has a wider bandwidth. We can do the same for the amplitude of excitation. As you might expect for a linear harvester, the bandwidth isn't a function of frequency or of the amplitude of excitation. Again, for the nonlinear harvester, it's a strong function of both. And it's only in these regions where we are exciting it very strongly and the frequency is high that it shows an improvement. So the clear conclusion from that was that if you want a nonlinear harvester to have a wider bandwidth, you must always consider this case where you have operation in this difficult to control multi-stable region. So we started to look at sort of parameter optimization in the case of nonlinear harvesters. So this graph here shows you the output power from your harvester with load resistance along this axis and frequency of excitation on this axis. And faintly in the background you can see a family of curves that represent the cases for a frequency sweep at different resistances. We then took a locus and the peak of those points, and you can see that peak projected. So the resistance versus power peak projection is shown here, the frequency versus power projection is shown here, and the resistance versus frequency projection is shown here. Now these look quite familiar, so particularly the resistance versus power projection looks similar to what you might imagine you would get for a standard linear oscillator being damped. But the twist here is that it's a function of all of both resistance and frequency at the same time. So if we take a slice through this plot, so we generally don't operate our harvester at different frequencies, it's at a fixed frequency, and you look at the trajectory of the optimal resistance for a fixed frequency, you end up with something that looks like this, and at another power level you can see something that looks like this. At a slice through in this direction, the frequency domain, we get that plot, and slightly higher we get the next plot. That's illustrated there. So I'm looking at the intersection of those power curves with a plane at a constant frequency. And we start to see one of the problems with these nonlinear harvesters is that we don't have continuous functions anymore for what might become our control variables. So if we wanted to control the output of a harvester, we might alter the effective resistance that it sees, presented by the converter, but that's no longer a constant function. It's not only is it not monotonic, but it actually has multiple solutions. Another way that you can think of this is that nonlinear systems are considered to have a backbone. So as we change the resistance, the damping applied to our harvester, we would see a series of curves, so A being the highest damping applied, B the next level of damping, C the lightest damping, and they correspond to a load that you would put to extract energy from this. And so what we really need to think about is that the frequency at which your energy harvester operates is tuned by the resistive load that you place on the end. So we've coupled now essentially the resonant frequency with the damping in a way that isn't coupled in a linear oscillator. Just to recap where we got to, and this was about maybe 10 years of research and a team of 3 or 4 people to get here. We know that a nonlinear harvester is only broadband in respect to a single frequency which changes over time. It isn't broadband in respect to multiple frequencies being presented together. But it still might be useful. There may be conditions where we might see a trajectory of a frequency, but it's a single harmonic. Several authors at this stage pursue stochastic models of harvesters, and if you follow that through, you have an interesting result that says the only thing that matters is the mass in the system and the power spectral density of your excitation. But it importantly neglects the fact that the reason we're using a resonant system is vibrations are small amplitude, and we need that larger amplitude of excitation in order to be able to extract energy from the system. But we also know that in order for our nonlinear device to be better than a linear device, we need to operate in this difficult region where there are multiple solutions. We know that we can come up with optimal load, we just showed there for steady state operation. But then another thing reared its head is that all of this analysis we presented is pseudo steady state. It doesn't consider the transient behavior of the harvester, which actually turned out to be extremely important. So where did we got to with our hardware? So this was some hardware we built, and this was it was built to mirror a flight trial that was going on. So my university, for insurance purposes, would not let my electronics fly, which is disappointing. So a company in the US made some electronics, and I made better versions of them to compare on the bench. Where we were, so we had our power conversion here, which had a synchronous rectifier at the front end. We then had a resistance emulating converter, so presenting a dissipative load to the harvester. We then had a variable voltage, a store, the supercap, and then a voltage regulator, and then feeding the sensor. This was operating around that sort of milliwatt to 10 milliwatt power level. It was all built from discretes. Where we were. One of the issues that when you're at that level, you generally need to make your magnetics large if you want to get high efficiency. So we could get in the high 80% efficiencies even at the milliwatt level by having large magnetics. Our harvester looked something like this. So this is determined by the seismic mass is determined by the amount of energy you want to get out from fundamental physics. The flight trial of this that flew on a helicopter didn't work. So what was found is that the power system periodically browned out during flight, and it turned out that what was happening is the power system had been designed with steady state excitation, but in a real flight the vibration level fluctuates, and that was causing the system to brown out, and then it wouldn't restart. What it turns out is that the dynamic behavior of oscillating systems and the associated power converter was causing a lot of problems here. This is a fairly sort of basic graph of energy harvesting from damping oscillators. This is load resistance and this is load power. And these sort of peak power curves are really familiar to all undergraduate engineers. But if you look in a system that has energy storage, like an oscillator, and you start to look at changing either the input or the output parameters, there's a trajectory that the system follows to get from one point to another. And that is different to the quasi-steady state trajectory. So the example we've shown here, this is the reference excitation here in terms of frequency and amplitude. And if you change your the frequency of your system, let's say you're here and the frequency increases by 5%, you want to transition to this curve. This is a quasi-steady state curve, and you want to get to this point here, and you'll have to follow this trajectory. If your frequency is decreased, then you would want to be following this trajectory along here. So this analysis is difficult enough with linear systems, but with nonlinear systems we hadn't found anyone who looked at these trajectories of parameters as you varied input and output parameters. This is some experimental work we did. We were looking at designing a maximum peak power tracker, and if you've looked at maximum peak power tracking from systems with energy storage, like a wind turbine and so on, you may understand that your system can seemingly extract a lot of energy by stalling the energy source. And this is an example in the vibration energy harvesting. So the same load resistance versus power. The steady state, quasi-steady state, is shown here in the thick black line, and these other lines are paired, and they are essentially trajectories. So this outer trajectory does this, and then like that, and that's looking at the load power when you sweep the resistance. So this is sweeping this resistance in 0.5 seconds. So we're going from 1,000 down to 100 here in 0.5 seconds. And what we see is a massive increase in generated power because we are essentially stalling the mass. We are extracting energy that was stored in that mass. And so if you can end up in a situation where if you have an algorithm that's implementing peak power tracking, it thinks you're going in the wrong way because it's seeing an increase in energy from that. We took this a bit further and we looked at it in terms of an energy harvesting system. So we said, let's have a system that, in theory, there is enough energy in the source, there's enough energy getting to the sensor node, and we showed on the top, this is an example. So the system has constant excitation, and it charges up. This is the voltage on the DC supply. It reaches a threshold, and then this dotted line indicates operation of the wireless sensor node. And it gets it's in a cycled operation. So essentially we have a duty cycled load, but a continuous input source. We then took that same system and we started to duty cycle the excitation. So now we have intermittent energy in and a duty cycled energy out. And what we found is in a real system, for relatively long periods of time, you'll note this is 60 seconds, so a minute here, so this is a period of seconds. We could induce operation where the system continually browned out and couldn't operate. And so this was what we thought was a fairly well-designed wireless sensor node, was incredibly susceptible to the dynamic interaction of the source energy and the load. And I guess these are the sorts of issues that power systems have all of the time. And in energy harvesting, we generally don't have the capability to store lots of energy in order to kind of damp out these vibration, these dynamic effects, to try and isolate the input from the output. Essentially what happens here is if you have any kind of rectifier, you're having your input impedance is a function of the stored energy in the system, and that creates these undesirable oscillations. So how about with nonlinear harvesters? Those two previous graphs were with linear harvesters. Well, not only now do we have to deal with these problems in the linear case, we also have trajectories of our parameter that we will control, i.e. resistance, that does something like this. And as yet we have not come up with a good way of coping with a parameter that has three possible states and controlling it and being able to understand it sufficiently well to do a design of the system. So where did we get to? So this is what I'm describing to you is a sort of 10 years of work. What we found is that the literature is full of nonlinear energy harvesters. There's a fairly low threshold for entry into doing this. You can just get a mass on a spring and shake it. So lots of people publish work. Nonlinear energy harvesters are a very rich area for our mechanical engineering colleagues who are interested in dynamics. And they have spent years developing tests and tools to analyze these. So they were producing a lot of these papers without really thinking of whether this was resulting in practical systems at the end. Very few papers presented a physical device, and even fewer present a device that is designed as a harvester that is anyway sort of packaged or could be considered a standalone device as opposed to just a laboratory experiment. And I would argue that no one has really tried to produce an energy harvesting system that takes into account the dynamic interactions of the source, the energy harvester, the electronic power conditioning, and then the old end wireless sensor node. But are they useful? So I don't want it to be too negative, this talk. It was a large part of my research career was spent looking at this. There are some important results. As we saw in the original MEMS work, it's quite difficult to make things that are small that conform to linear approximations. So by understanding the effects of nonlinearity, we're already better placed to work and build MEMS scale devices. We need to understand these, whether we want them to be there or not. From the steady state characteristics, we think that probably they are beneficial in certain situations. The idea that they have a broadband response in terms of being able to respond to multiple frequencies at once, that's probably not going to happen because they are so sensitive to the relative phase of those harmonic components. But they still maybe have some use. And ultimately, it was unclear to us that this, I put it there rather long-winded, that the real behaviour is so much more complicated than we were considering our analytical models. And it's not clear that we were able to draw sufficient conclusion from that to be able to design a system, particularly in this case of variable load and variable excitation. And so there we have it. We have a trajectory through, and not necessarily a happy conclusion, but then research isn't always that way. So does anyone have any questions?
Any questions or opinions or something else?
I have a question. Why do you choose this kind of approach, the magnetic?
So that was really dictated by the size. So when you shrink down, perhaps electrostatic can be more favourable. Magnetics scale with the volume scaling law, so that their effectiveness falls away. Piezoelectric is the other very popular conversion mechanism, but that produces, there's so much capacitance in the output of those that you spend all your time trying to compensate for that very capacitance, that very capacitive output impedance. So although they aren't particularly considered, that cutting edge, sometimes people look down their nose at springs and magnets, they're often at this sort of scale the right solution.
Yeah. So, what is your opinion about the future of energy harvesting in industry, in life?
So in the UK we have a company called Perpetuum who commercialised this sort of scale energy harvesters, and they struggled for a long time. They went for several years trying to find a niche, and eventually they found it monitoring railway locomotives, and they have become very successful now selling a complete system and a service that bolts onto the axle of a railway carriage, and it powers itself from the vibration, and it measures for wheel flats, and it can detect damage to the track. But the conclusion from that is no one really wants to buy an energy harvester. It's too complicated. But they are very happy to buy the services that you can provide with an energy harvester.
May I ask?
Yeah, of course.
As I know, energy harvesting is one of the ways for development of Internet of Things.
Yes.
So, energy harvesting is obliged to be successful. It is obliged to be successful.
I think there is a tension. So what we're seeing now in the field of Internet of Things is that there's maybe a feeling that devices that are designed specifically, wireless sensors, aren't making much impact, and that maybe the types of media terminal that we have, like mobile phones and tablets, could be sort of repurposed and made energy autonomous.
Yes, but mobile phones and such wearable computing, they need to charge their batteries.
Yes.
But a device which is anywhere, there is nobody to charge its battery. It must be supplied by itself. So this is
You're right.
This is the trend for energy harvesting.
You were right, and that's why I had those slides at the beginning of working through the power consumption, because if I just gave the talk on energy harvesting, you'd think, why did anyone bother? Why would anyone go to that trouble? But there are certain things that we'd like to do that just can't be done with energy storage. Very long-term deployments, remote areas. And one of the things that we've chatted about over the last few days with my time with Cerno from Analog Devices is that often people design the functionality and then the power consumption is a consequence. And the power consumption is always too high. But if you design balancing functionality with power consumption, you don't get everything that you want in terms of functionality, but you may get a viable system.
Maybe let me say a few words. You see, some of frequency responses which you showed here,
Yes.
looks somehow familiar for me, but in some other area.
Yes.
In fact, active filters
Yes.
with active devices, their frequency responses have the same behavior when appears the non-linearity. It moves to one or other side of the to downside or upside.
Yes.
Exactly like in your case. It's very interesting, but maybe it's based to the similarity of the differential equations which describe them.
Yes, I think you're right. Yeah, and if your stiffness gets greater with displacement, it curves the frequency response one way, and if it gets softer, it goes the other
It's possible also
Yeah.
to go downside.
You can create quite complicated responses that soften and then harden.
Yeah.
And then
I saw it
you
also.
get this, yeah.
It's basically based. A few years ago, we have some project with a student which showed exactly this behavior in this way, and that after that it returns.
Yes.
Very interesting.
And
It
you
was.
can get some very interesting sort of isolated responses that can't be reached
Yeah,
from the main branch.
Yes,
Yeah.
it can be reached. Practically, it appears in the frequency response measuring
Yes.
like a jump in the frequency response.
Yes. Yeah.
So I have a similar question to that. So you tried to control the resonance by controlling the damping, which is the...
So the damping is always a proxy for the electrical load in most cases.
Right, but
So
it's,
you have a-
yeah. So it's controlling it using kind of the energy loss mechanism in the system. But did you consider maybe adding energy so that you can sustain the resonance?
Sure. So I think you have a different mindset if you're interested in information, then you have a different mindset to if it's energy. So you could force a system to have a very interesting frequency response if you weren't interested in the energy. But because you want to end up with a net positive energy out, if you think about putting energy in, then I'm trying to recall.
I don't mean to form a perpetual motion machine, but if you're at the peak, at the resonance peak, and you just want to control staying at that peak, you only need a negligible, but you need a finite amount of energy to keep the system stable there. So maybe the amount of energy you add is less than the potential benefit.
So in an oscillator, you can use the amplification as a proxy. It's the ratio of the Q, it's the ratio of the energy out to the energy in. So if your non-resonant behavior is down here and your resonant branch is up here, then to jump from here to here requires you to put in maybe 10 times the energy that is being damped in this condition. So your energy you put in is very large compared to the average energy of the system. And you have to put it in at the right point so that it has to force the oscillator not only up in terms of its gross amplitude, but it has to achieve that at the right phase in its relationship for it to be stable, or it will just immediately drop down again. So you're putting in very large amounts of energy, and it's very difficult to control it to be stable. So my link to your question as well, my colleagues in mathematics perform an operation called continuation, which enables you to track out the unstable branch. And some of them have implemented that physically, so they have a controller to hold the by modulating the base excitation, you can control the harvester to be on that unstable branch. But it isn't, it's a very inefficient way of doing it. You're putting in a huge amount of energy to hold it on that unstable region.
Have you ever tried to modify the converter? You said that's really interesting that the input impedance of the converter,
Yes.
it's in function of the energy that is stored. Have you ever tried to modify the frequency of the converter? There was a really nice paper from, I think, Chandra Kasan, 2009, that he modified the frequency of the energy converter, which modifies the input impedance which the harvester sees. Have you ever tried some kind of this?
Yeah, so we built the converters we tend to use here are resistance emulating converters. We have built a variable power factor converter which can try and tune, but again, that's if you're trying to make a variable power factor converter at a milliwatt, it's quite tricky, right? Because you have your PWMing, so you have switching going on and device losses, and that approach directly, it can work, but it has limitations, because there's also, when you start to frequency tune these devices, you have lots of circulating energy, and so your circulating energy again might be an order of magnitude higher than your useful load energy, so you become very sensitive to conduction losses. But in piezo devices, you have a similar problem, not trying to tune the mechanical side, but trying to resonate out the capacitance in the output impedance of the piezoelectric device. And so people use a variety of nonlinear approaches, synchronous switched inductor, and which are sort of approximations to that variable power factor approach. So I could have maybe given you a different presentation on those things as well. Yeah. The challenge is really a lot of these things can be done at large power levels. It's not used to make a converter with a variable power factor input. But when you need to do it at a milliwatt of power, so the losses must be fractions of a milliwatt, it becomes really challenging.
Other questions, please?
Have you ever tried something about reverse electrolytic on dielectric harvester based on reverse electrolytic? You have a dielectric and, for example, water, and then you move the two plates, and the capacitance changes. It's basically electrostatic.
Like electrostatic with the dielectric. Yeah. So I guess if it was in a fluid, you'd have a lot of losses in the fluid. I think one of the issues that the transduction coefficient is nonlinear with yeah. So
because the area of the droplet changes and changes the capacitance of the system.
Yeah. So I think in the past, several researchers thought that electrostatic type conversion would be the way to go. I think when people have tried to implement variable capacitance devices at MEMS scale, and they use them for power, the electrostatic forces associated with the bias voltages tended to destroy the devices.
Yeah.
So this is third-hand or second-hand information. So I think that area of research was found to be problematic. There's some colleagues of the power MEMS community in Japan who make electret-based harvesters, and they have a commercial device, so they're quite robust, and they seem to have made it work quite well.
The electric material is quite tricky to make it.
Sure, yeah, I guess that's their expertise. Yeah, yes.
Maybe.
Well, thank you very much for your attention. I'm afraid my Bulgarian is so terrible, you wouldn't have understood anything, but hopefully you understood a little bit. I'm very happy if anyone is interested you can email me or grab me at the end. Thank you for your attention.
Thank you.
So, thank you, Mr. Burrow, for your interesting lecture, and we are expecting you again here in Bulgaria.
Great. Thank you very much.